my name is Ilia Malakhov, and today I would like to present you our project, kotlinx.fuzz, and how we are bringing fuzzing to Kotlin. First of all, I will introduce you what fuzzing is and why are we needed. Then I will dive into what actually is our project, and then I will overview our challenges and some interesting features. First of all, what actually is fuzzing? Well, the fuzzing comes from word fuzzer. And fuzzer is a tool that finds bugs in programs by executing them on some random inputs. And well, actually, this definition gives us a black box fuzzer. Fuzzer that doesn't require any information about the program. However, we can make some other different fuzzers, like white box, which has full information about program, or gray box, which has some of it. As you can imagine, black box are very simple and stupid, but they are also very fast. White box, on the other hand, are very advanced, but also requires a lot of time to get some results. The gray box are in the middle, and they are very good, since they are efficient like black box, but much more effective. A lot of gray box tools use coverage to guide their execution. This gives us a coverage-guided fuzzer. Here you can see how such fuzzers work. So they basically generate some random input, then they execute program with this input, and then they check if they covered a new line during this execution. If yes, then this is good, and we save this input. Otherwise, we just forget about it. Next, we see what input we have saved from the past, select one of them, and generate the new input somehow. And then we repeat all this cycle again and again until we reach the timeout. To better understand it, let's consider an example. We have some test which gets an integer from the fuzzer, and then there is just some code. First, fuzzer will likely to generate a 0 as this integer, which gives us coverage of this line. Next, let's say it mutates 0 to 2, and this gives us another line. Then it may mutate 2 into 4, which leads to this line again. And as you can see, we doesn't save 4 to our inputs. We just forget about it. Then we generate 3, which is also good. Then something interesting happens. We generate 6, and this leads us to the exception. So we save 6 as crash, an input which leads to some error. Then we generate 8 from 6, which doesn't give us anything new. Then we generate 9. And finally, we generate 12. And let's say at this moment we run out of time. So we provide users this 6 as some crash. Now, when we understand what fuzzing is, let's talk about kotlinx.fuzz. With this project, we want to develop a fuzzer which should be applicable for any Kotlin program. Shouldn't be specified for anything. Should be useful for a lot of developers, and it should be actually useful for them. And this fuzzer should be specifically designed for Kotlin, so it understands its specifics, since Kotlin has a lot of features. We need this because we have some teams at JetBrains which are interested in bugs, which can be found by Fuzzer. And they also need tooling to run this Fuzzer. They tried to do this on their own, but they have failed. On the other hand, we have experience in fuzzing, and we can do this. Ideally, we just want to get something which can give us results. However, that is not realistic, unfortunately. So let's say we want a tool, we want an API to write fuzz tests, we want some Gradle plugin to be able to run these tests, and we want this to be convenient. So for example, we could debug these tests in IDE without a lot of effort. First of all, we realized that writing own Fuzzer from scratch is very hard and takes a lot of time. So we search for existing tools. Such is, for example, Jazzer or JQF. Both are coverage-guided gray box fuzzers. We evaluated them, and the best one was Jazzer. It uses libfuzzer, another fuzzer, but for C++ program, which is very good. It also has some basic integration with the Java and Kotlin ecosystem, such as with JUnit. However, it has a lot of drawbacks. The most important one is that it can fuzz multiple tests simultaneously. In our experiments, we found out that to get some results, we need to spend at least several hours on fuzzing. For the single library, we usually had around 10 fuzz tests. So without paralleling this process, it takes too much time. Another thing is that it has some issues with Kotlin features. For example, it usually counts coverage of inline functions incorrectly. Another thing is that all these integrations are actually very tricky. They use some hacks to work, and it would be very hard for us to extend them. Before I dive into the specifics, we need to understand one important thing. When I previously showed an example with fuzzer generating integer, internally, this fuzzer doesn't generate integers. Instead, it generates some byte arrays, some raw data. So to overcome this, it provides fuzz data provider, which essentially just parses this byte array into something more meaningful like primitives or strings. So you can see this example. We have fuzz data provider. Internally, it has some byte array like this. And when we just do some call, it just looks at this byte array and passes some bytes into primitives or strings. Now, when we know the specifics, this is actually how we have to use Jazzer. There is 9 steps, and as you can see, some of them are like this one, are not very much related to fuzzing, but like I said, without this script, the fuzzing time increases dramatically. So we have to do it. Despite that, we successfully applied it to 8 kotlinx libraries. We found more than 20 bugs. Most of them were accepted and fixed. And we get a lot of experience and understanding how can we improve things. Let's consider the example of the test we made for kotlinx datetime. Here we have our first data provider. We consume some string from it. Then we parse it using Kotlin method and using Java method. Essentially, they both should return the same duration. So we have an assertion to actually check that. However, when we spend 30 minutes fighting these tests, we find 2 things. First, with this string, Kotlin fails to fuzz it, to parse it. However, Java successfully parses it as an empty duration. And this is actually a bug in Java standard library. So, well, when we fuzzed Kotlin, we find bug in Java. On the other hand, with the second string, Kotlin parses it as -2 hours, while Java fails. And this time, Java's behavior is correct, and this is fixed bug in Kotlin standard library. To sum up, Jazzer is actually working. It can find real bugs in real Kotlin projects. However, usage is very painful and a lot of things are made suboptimal. Luckily, we can do better. And here comes kotlinx.fuzz. We ended up with 4 main components: an API to write fuzz tests, a plugin to actually run all of them, so we don't need all these scripts. We have JUnit engine to integrate, which is used by our Gradle plugin, but it also allows support for ADEs and other build systems than Gradle, at least theoretically. And we finally have Jazzer as the fuzzer. So we actually can utilize all the good things from it. First of all, in the API, we have essentially 2 main things. First of all is a fuzz test annotation, which is just an annotation to mark fuzz tests. And then we have kfuzzer, which is our reimagined version of fuzz data provider, which has, in our opinion, better interface than them. Noticeably, it uses Kotlin features like ranges. We made our own new features generating string by regex. And this is our current version, but we have plans to add more things to it. Here you can see the comparison between our API and Jazzer API. You can see how the code on the left side is shorter and more convenient. For example, here you can tell does this function include 22 to their possible results or not. I don't remember what it is. And also, we have better support for nullability and some extra features. The next thing is Jazzer. to actually allow fuzzing multiple targets at once. For every test, we just spawn a new process with Jazzer. So we didn't heavily modify Jazzer but instead we just make a better tooling around it so it can be used this way. Also, we actually patched Jazzer to add some more features. One of them is better crash deduplication, which I will dive into later. And the other thing is Linux IRM64 support, which we are working on now. For genuine integration, we first of all for genuine integration, we have wrote our own test engine. The bottom genuine version is actually a platform which provides interface to IDEs, build tools like Gradle, and etc. And the test engines which actually execute the tests. So for ourselves, we made kfuzz engine, which allows executing fast engine tests. So yeah, this basically need to do two things. First, it need to discover tests, which is basically just filtering them by annotation and type parameters. And then we need to execute tests. So this engine setups fuzzing fuzz engines, essentially Jazzer, and then it delegates all the execution to Jazzer. One more thing to note is that we also support tests written with Jazzer API. So basically, if somebody supports Jazzer in their project, they can easily switch to our fuzzer and get smoother migration and much more new features. Last thing is Gradle plugin, which provides two things. First of all, it provides tasks to run all the things. And after it runs all the things, it generates reports. And it also has a DSL to configure our fuzzing. This DSL looks like this. In Jazzer, for example, you had to use either environment variables and store it somewhere, or use unit properties, which is not very convenient, since it doesn't allow to check it for errors. And this is how kotlinx.fuzz can be used. As you can see, there is a little less steps than with Jazzer, but actually some of the later steps are also much easier. Actually, after you wrote all your fast tests, you just need to run it and get some results, which you can use later, which was not so true with Jazzer. Now, the final thing is our new features and challenges. Let's get into them. The first one is crash deduplication. Although fuzzers can find a lot of bugs, they can also find one bug multiple times. And this can really slow down the later analysis and debugging. So to overcome this, we can make the fuzzer to understand if it found its crash multiple times and do something with it. The simple approach used in Jazzer is just to compare stack traces by equality. So if two stack traces are equal, then this is the same crash. However, this is implemented poorly and doesn't work well. For our project, we found out a library with which compares stack trace, which can compare stack traces not strictly, but to some extent. It's a very intelligent way, and it works much better. The next thing is that although our kfuzzer interface is really good, it still requires some effort to use it. What if we could allow our users just to write some parameterized tests where they just accept some primitives and even more complicated objects, and then let fuzzer to fuzz it. Jazzer has such feature, which is called afterfuzz, but it is extremely limited. It can find a constructor or fabric method for the class and then call it by providing parameters from fuzzer. But since these methods usually have some invariants and argument checks, this thing works poorly. In our project, we are also going to have such feature, but with some more API to control it and guide it to be more useful. So on the left, you can see the tests with kfuzzer, and on the right, you can see the same test written with afterfuzz, as we expected. The next interesting feature is hooks. Let's consider some code. It accepts some user input, and then it does something, and at the end it executes command. The question: can this command be something unexpected and malicious? To find out, let's do the trick. Let's insert the assertion which checks if this command is something completely unexpected. So the users don't expect the kfuzz command to be executed. What will happen if fuzzer if this assert fails during fuzzing? This means that some user input can lead to this command. Since this is some arbitrary command, this means that we can execute arbitrary commands. And this is very likely to be a vulnerability. So this, which is a bug, and it should be reported and fixed. So hooks can find such vulnerabilities very well. And we want to provide two things. An API for users so they can write hooks for their libraries. And we also can provide some hooks for some existing libraries and methods so users actually don't have to do anything to find such bugs. Another thing is crash reproduction. After fuzzer successfully finds a bug, the user then need a way to debug this bug. To open it in IDE, set a breakpoint, and go into. So the crash reproducer is basically a test case which and reduce this crash behavior. For example, this is the crash reproduction for the bug in the next daytime I about later. The problem is achieving such ideal result is very hard. So we started. The first idea is just record values which kfuzzer returned during execution. Then we just create kfuzzer from these values, and then we just called original fuzz test. And this is what we already have. The next step is to actually inline the user's fuzz test. So we can have both the code and the values on the same screen. So the previous result will like that. We just final step would be to completely completely get rid of our kfuzzer API. It means that we have to somehow find kfuzzer calls and replace them with constant. It should look like that. This is very much complicated, but we will do it. One more thing is oracles. As I have shown, writing fuzz test is actually not so hard. However, to write one that finds a bug is more complicated, because the test need to somehow determine if it finds an error. The first idea is that it can check for exceptions, which is most of our tests. The problem is that some exceptions are actually expected and don't mean that this is a bug. So users still need to write some code to filter good exception from bad and so on. The better approach is to find some analog library and compare the result with our library. This actually works well for Kotlin because there is a lot of Java libraries. However, some Kotlin features are not present in Java. For example, Kotlin you can write a DSLs. So there is no analog in Java to compare with. As you can see, there is no idea to make this without user's effort, which is very unfortunate. So our plans is to finish our work on reproducer generations, to make some out-of-us mod, to design hooks for our library, and to release version 1.0 at the end of the March. The last thing I want to tell you is that this tool is already working. You can add it to your Kotlin project and use it. So I highly encourage you to do it. We would be happy to support you with that. Thank you.